For decades, we were taught the universe is uniform on a grand scale. This was the foundational principle of cosmology. Wherever you look, everywhere is the same. We were wrong. In 2013, scientists proved that we live at the near-exact center of a giant void, 2 billion light-years wide. This is an anomaly where matter is 20% less than it should be. So, when we measure the expansion rate of the universe, we find impossible numbers that break our fundamental equations, because we are not measuring the universe as it should be. We are measuring it from inside a hole. If you're ready to see how everything you thought you knew will be shattered, then hit the like button and subscribe, because the end of the standard model is here. Are you ready? We begin. The world of science believed the universe was smooth and uniform on a grand scale. This was the cornerstone of cosmology. No matter where you looked, once you zoomed out far enough, the distribution of matter was supposed to be roughly the same. This was called the cosmological principle, and our equations were built on this assumption. But 3 astronomers, while counting galaxies in 2013, noticed something that shattered this principle to pieces, an anomaly, an impossibility. And in that moment, everything changed, because now we know we do not live in a typical corner of the universe. We are at the very heart of an exception. This exception has a name, the KBC void. This is the massive cosmic desert we are swimming in, 2 billion light-years wide. 2 billion. It is difficult to even imagine that number, but the truly shocking thing is not its size, but its content. The amount of matter in this enormous volume is a full 20% less dense than the rest of the universe. This is not a small deviation, this is a giant anomaly that standard cosmology models struggle to explain. When computer simulations model how the universe has evolved since the Big Bang, they almost never produce a structure this large and this empty. According to some scientists, the existence of such a void corresponds to a 10 sigma statistical deviation. What does that mean? It is so rare that you should not expect to find even one in the entire observable universe. But we did not just find one, we live right inside it. So what does living inside this statistical nightmare mean for us? This is not just a distant astronomical fact. This is a reality that directly affects every single measurement we make, every single day. This effect manifests itself in one of modern cosmology's greatest crises, the Hubble tension. For years, scientists have been measuring the expansion rate of the universe with 2 different methods, and finding 2 conflicting results. The first method looks at the cosmic microwave background radiation, the light released when the universe was only 380,000 years old. The analysis of this ancient light tells us the universe should be expanding today at about 67 kilometers per second per megaparsec. But the second method makes a direct measurement by looking at supernovae and stars closer to us. This local measurement consistently gives a higher number, around 73. The difference may seem like 9%, but this is not a small discrepancy, it is a crisis, because both measurements are incredibly precise, with very low error margins. Statistically, the chance of this contradiction being a fluke is less than 1 in a million. This is precisely where the KBC void comes into play. If you're inside a giant void, the gravity of the denser regions around you pulls you outward. This adds an extra kick to the local expansion. That is why our local measurements are coming out higher than the true expansion rate of the universe. The equation is not wrong. Our location is. So is this giant void the only anomaly in the universe? Absolutely not. In fact, the universe itself seems to be an anomaly. Because the universe is not an ocean filled with galaxies. It is a foamy structure, riddled with giant voids, with walls and filaments made of galaxies. We call this the cosmic web, and it is the largest structure in nature. Almost this entire structure, 90% of its volume, is made up of voids just like ours. All the galaxies we see, know, and measure, all the clusters and superclusters, are located on the thin walls and filaments between these immense voids, in that remaining 10%. The scale of this structure is mind-boggling. For instance, A galaxy filament known as the Sloan Great Wall is about 1.5 billion light-years long. But even that is dwarfed by the voids. Structures like the Eridanus supervoid can reach 1.8 billion light-years in width. So, galaxies are not the fundamental building blocks of the universe. They are just bright markers, showing where matter happened to clump together. The real structure is the voids and walls themselves. We do not live in a universe full of galaxies. We live in a universe of voids, with occasional encounters of matter. So what do we have? A statistically impossible void surrounding us. A measurement crisis, caused by this void that refutes our most fundamental equations, and the fact that all of this is just a small part of a colossal network of voids, making up 90% of the universe. Were these structures, these enormous pockets of nothingness, there from the very beginning? Or did something go horribly wrong in the history of the universe to create these monsters? Are these giant voids and the walls surrounding them the result of a plan that existed from the very beginning of the universe? Or is it all just a coincidence that developed later? Because these colossal structures are the result of a plan that was in place from the very beginning. It all started with seeds sown in less than the first second after the Big Bang. At that moment, the universe was not perfectly smooth. Quantum fluctuations caused some regions to be a fraction denser than average, and others a fraction sparser. The differences were incredibly small, perhaps 1 part in 100,000. But gravity, over time, turns even the smallest advantage into a massive difference. This process is a snowball effect. Gravitational instability. The regions that were initially slightly denser pulled in more matter from their surroundings. This made them even denser. This positive feedback loop continued for millions of years. Dense regions merged to form first stars, then galaxies, then clusters of galaxies. Meanwhile, the regions that were initially slightly sparser continuously lost matter to their neighbours. As matter flowed towards the dense regions, these sparse areas became even emptier, eventually turning into giant voids. The cosmic web is a masterpiece, patiently crafted by gravity over billions of years. It transformed those almost imperceptible quantum fluctuations at the beginning into the magnificent architecture we see today. This is why voids are not the boring crystallized inert parts of the universe. They have been part of the story from the very beginning, and their evolution is so important it could fundamentally shake our understanding of the universe. Because in these voids, gravity does not work as we know it. The gravity inside voids does something completely counterintuitive. Instead of pulling inward, it pushes outward. This does not mean the law of gravity is reversed. Gravity always pulls mass toward mass. But here, geometry is everything. Imagine yourself standing at the center of a vast valley, surrounded by high mountains. Where does gravity pull you? Towards the mountains. That is, away from the center of the valley. Galaxies inside a cosmic void experience the exact same effect. Almost all the matter in the universe is concentrated outside the void, in the surrounding filaments and clusters. This external mass pulls everything inside the void towards itself. The result is a systematic outflow, where galaxies accelerate from the center of the void outwards towards the denser regions. This is not a theory, this is a measurable fact, and the speed of this flow is dizzying. Our own galaxy, the Milky Way, is moving away from our nearby local void at a staggering 600,000 miles per hour. That is about 850 times the speed of sound. This motion is a result of local gravitational imbalance, completely separate from the overall expansion of the universe. But these voids are not entirely empty, which makes them even stranger. Rare galaxies and clouds of hydrogen gas drift within them. But their main inhabitants are the dark side of the universe, dark matter and dark energy. In dense galaxy clusters, gravity wages a war against the expansive effect of dark energy. But in voids, matter is so sparse that gravity loses this war from the start. So, in the voids, the winner is clear, dark energy. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward. This creates another feedback loop. The more a void expands, the emptier it becomes, which allows it to expand even faster. This is why voids are the best laboratories in the universe for studying the nature of dark energy. Because they are the only places where gravity whispers and dark energy roars. So what do we have? Giant voids, born from quantum fluctuations, covering 90% of the universe. The strange geometry of gravity within these voids, pushing matter outwards. And because of this pushing force, our galaxy is moving at the incredible speed of 600,000 miles per hour. Furthermore, there is the fact that these voids are natural laboratories, dominated by dark energy, expanding faster than the rest of the universe. As consistent as this entire theoretical framework may sound, one question hangs in the air: where is the proof? Do the observations truly support this strange and unsettling picture? How did scientists discover the existence of this giant void, these insane speeds, and this weird physics? And now comes the real shock, because Kirsin, the evidence supporting this theoretical framework, started coming in one by one from the most unexpected places. These are not just small clues, these are undeniable, earth-shattering facts that shake the very foundations of cosmology. Here are the findings. It all started with 3 astronomers doing an extremely mundane job: Ryan Keenan, Amy Barger, and Lenox Cowi. In 2013, they were simply counting galaxies. They were mapping the positions of 35,000 galaxies across billions of light years. But the numbers were wrong. They were impossibly wrong. Everywhere they looked near Earth, there were fewer galaxies than there should have been. Not just a few less. A full 20% less. This anomaly was not in a single direction either. It stretched out in every direction for 1 billion light years. Before their very eyes, a giant spherical void was emerging, with us almost at its center. This was not a small gap between galaxy clusters. This was nothingness on a scale that, according to standard cosmology, should not exist. The researchers triple-checked their data. They used different galaxy surveys. They studied the sky from different angles. But the result did not change. Our galaxy, and everything around it, was sitting inside a colossal, under-dense bubble of space that dwarfed everything we had ever observed. This discovery was named the KBC void, after the initials of its discoverers. But this ordinary name could not hide the revolutionary truth it represented. This was not just an anomaly. This was the first concrete proof that the window through which we view the universe is warped. But this void did not just reveal itself in galaxy counts. It had also left its mark on something much older, much more fundamental: the first light of the universe. The cosmic microwave background radiation is the faint afterglow of the Big Bang, providing a temperature map of the infant universe. Theoretically, photons from this light should lose energy as they pass through a giant void, causing that region to appear as a cold spot in the sky. This is known as the integrated Sachs-Wolf effect, a hard-to-prove but inevitable physical consequence. For years, this was just a theory. But then scientists overlaid maps of large voids with the cosmic microwave background map. The result was perfect. The observed cold spots aligned exactly with where we now know the great voids are. This was not a coincidence. This was physics itself. While the effect created by the KBC void around us is not a single giant cold spot in one direction, it subtly altered the overall patterns in the universe's temperature map. This was further proof that the void is not just a structure that exists today, but is massive and influential enough to have changed the fate of light during its 13.8 billion year journey. A void our eyes cannot see had left its mark on the oldest light in the universe. And then there is our speed, the motion of our galaxy. According to standard models, if the universe were truly homogeneous, our peculiar velocity, our motion apart from the expansion of the universe, should be quite small, perhaps 100 or 200 kilometers per second. But the measurements showed something entirely different. The local sheet, which is made up of our galaxy and its neighbors, is moving away from the center of the nearby local void at about 260 kilometers per second, or 580,000 miles per hour. This alone is a much higher speed than expected. But that is not all. When you add up all the gravitational effects, the Milky Way's total peculiar velocity relative to the cosmic microwave background reaches 627 kilometers per second. That is over 1.4 million miles per hour. Why are these numbers so shocking? Because just to have such a high velocity, there must be very strong gravitational gradients nearby. That is, a huge deficit of matter on one side and a huge excess of matter on the other. Exactly the kind of scenario you would expect when standing on the edge of a giant void. Our motion is the most dynamic evidence of the void's existence. We are not passively drifting in an expanding universe. We are rolling down a giant gravitational slope at an unbelievable speed. So what do we have? A giant void stretching in every direction, containing 20% fewer galaxies than there should be. A cold, ghostly fingerprint left by this void on the oldest light in the universe, and a speed unpredicted by theories exceeding 1 million miles per hour, caused by the gravitational imbalance of this void. When these three pieces of evidence are combined, they point to one unsettling conclusion: the cosmological principle, at least in our neighborhood, is not valid. But could there be a deeper connection that ties these seemingly independent pieces of evidence together, making them all part of one grand picture? And yes, there is a deeper connection that ties these pieces of evidence together, making them all part of one grand picture. This connection is hidden in one of the most fundamental scales of the universe, in sound itself. In the first 380,000 years of the universe, everything was a hot, dense soup of plasma. Within this plasma, sound waves propagated just like in air. These waves froze in place when the universe cooled and atoms formed. But they left a trace behind, a characteristic scale in the distribution of matter of about 490 million light-years. This is a cosmic ruler known as baryon acoustic oscillations, or BAO. This ruler is universal. Whether you look at nearby galaxies or those billions of light-years away, this 490 million light-year pattern should be there. But it is not. When scientists analysed the galaxy distribution in our local region using this cosmic ruler, they found a clear deficit. The void revealed itself as a region where the scale of galaxy clustering was different from what distant measurements predicted. This discrepancy is exactly the kind of result you would expect when you're inside an underdense region. Baryon acoustic oscillations provide completely independent evidence for the existence of the void and confirm its depth and size. The universe itself was telling us we are in a void, through a ruler etched into its own fabric. But the evidence does not end there. Perhaps the most disturbing lies in the phenomenon known as the Hubble bubble. When astronomers measure the Hubble constant using nearby objects within about 2 billion light-years, they consistently find a high value around 73. However, when they use objects farther than 2 billion light-years, or rely on data from the cosmic microwave background, they get a lower value around 67. This 2 billion light-year boundary is not a coincidence. It suspiciously corresponds to the edge of the KBC void. This situation led to the hypothesis that our measurements inside the void are affected by its presence, creating a bias bubble. We can only see the true expansion rate of the universe by looking outside this bubble. This hypothesis makes a clear prediction. The measured Hubble constant should change with distance. Nearby measurements should show the highest values. The value should decrease as we approach the edge of the void and stabilize at the lower value beyond 2 billion light-years. And recent observations are beginning to show exactly this trend. This means our most reliable local measurements are the very ones most affected by the void. We are trapped inside the bubble, unable to step outside to understand what the universe truly looks like. And finally, there are the large-scale motions, the bulk flows. According to standard cosmology, the average motion of galaxies in huge volumes hundreds of millions of light-years across should be close to zero. Because, in a homogeneous universe, there should be no large-scale gravitational gradients to pull them in a specific direction. But observations once again demolish the theory. Galaxy velocity measurements using multiple techniques show significant bulk flows, extending to distances of 200 to 300 million light-years. These flows reach speeds of 400 kilometers per second or higher. This is much higher than standard cosmology predicts. On such large scales, huge volumes of galaxies are all moving in roughly the same direction. This is the kind of flow a structure like the KBC void would generate. The material inside the void is accelerating outwards towards the denser regions beyond the void's edges. This creates a bulk flow pointing away from the center of the void, and the observed bulk flows match the predictions from models that include the KBC void. A 20% density deficit spread over about 1 billion light-years produces exactly the observed flows of 400 kilometers per second. So, what do we have? An anomaly revealed in the BAO, a ruler etched into the very fabric of the universe. A bubble effect appearing right at the edge of our void, between distant and nearby universe measurements, and rivers of galaxies, flowing for hundreds of millions of light-years, which standard models cannot explain, but the void hypothesis explains perfectly. All these pieces of evidence, though independent, scream the same uncomfortable truth. We are not ordinary inhabitants of the universe. We are inside an anomaly. So how exactly does the physics inside this vast nothingness, this cosmic desert, work? How does gravity manage to push? And what role does dark energy play in this equation? So how exactly does the physics inside this vast nothingness, this cosmic desert, work? How does gravity manage to push? And what role does dark energy play in this equation? Now is the time to slow down the pace of shocking discoveries a bit, and look under the hood of this strange universe. Because, once these mechanisms are understood, it becomes much clearer just how bizarre and counterintuitive a place the universe is. The first mechanism is the illusion of inverse gravity. At the core of this illusion lies the fact that voids are not actually completely empty. They still contain some dark matter, dark energy, and sparse gas clouds. However, this amount is far below the universal average. The dark matter density inside a void is about 15% of the cosmic average. This means there is still some gravity. But the real issue is where this mass is not. Just like the holes in a sponge, the real matter is in the sponge itself, not in the holes. The filaments and walls outside the voids contain most of the universe's matter. Their density can be up to 3 times the average. So, a galaxy inside the void feels an unequal gravitational pull from all directions. Inward, towards the center of the void, there is very little matter pulling it, but outward, towards the edges of the void, there is the overwhelming gravitational force of massive galaxy clusters and filaments. As a result, the net force is outward. Gravity does not push, but the geometric distribution of mass forces everything inside to fall outwards. This effect is strongest at the center of the void and weakens towards the edges. Therefore, the velocity profile of galaxies inside a void is complex. Those at the center move outward fastest, while those at the edge move slower. This mechanism explains why we measure the Hubble constant differently depending on distance. Most nearby supernovae are in the region where this fast outflow is strongest, so our measurements are artificially inflated. The second mechanism is the triumph of dark energy. Gravity is the weakest fundamental force in nature. It needs massive objects like planets or stars to show its effect. In a void where matter density is very low, gravity becomes even more insignificant. In this case, the most mysterious component of the universe takes the stage: dark energy. Dark energy is an repulsive pressure, inherent to the fabric of space, that accelerates expansion. In dense regions, gravity fights against dark energy and slows down the expansion in those areas. But in voids, this battle is one-sided. Gravity is so weak that dark energy wins an overwhelming victory. The result of this victory is that voids expand faster than the rest of the universe. This creates a self-reinforcing cycle. As a void expands, it becomes even emptier, which weakens gravity even more and allows dark energy to become even more dominant. This shows that voids are not just passive empty spaces, but active and dynamic components of the universe. They are expanding bubbles, growing over time by eating the surrounding filaments. This mechanism explains why the future of the universe will be an increasingly empty and isolated place. Billions of years from now, if dark energy continues to dominate, the filaments will thin out and galaxy clusters will become isolated islands in an expanding ocean of nothingness. The third and perhaps most fundamental mechanism is the legacy of initial conditions. These colossal structures we see today did not appear later. Their seeds were sown in an unimaginably small moment, something like 10 to the power of minus 35 seconds after the first second of the universe, during the period called inflation. During this period, the random fluctuations of the quantum world were stretched from subatomic scales to cosmic scales. This caused the density of some regions to be a tiny fraction higher than average, like 1 part in 100,000, and some to be lower. And it all started with this tiny difference. After inflation ended, gravity amplified these initial density differences over billions of years. Dense regions attracted more matter to form galaxy filaments, while sparse regions lost matter and turned into voids. The cosmic microwave background radiation provides a snapshot of these density differences when the universe was 380,000 years old. The hotspots on the map correspond to the dense regions that would later become galaxy clusters, and the cold spots to the sparse regions that would become voids. When computer simulations take this initial map and fast forward it billions of years with the laws of gravity, a structure very similar to the cosmic web we observe today emerges. This shows that our theory is largely correct. But there is a problem. These simulations rarely produce a void as large and deep as the KBC void. This suggests that either the initial quantum fluctuations had different patterns than we thought, or gravity works differently on large scales, or we are just incredibly unlucky and live inside a statistical anomaly. So what do we have? A strange dynamic inside voids, where gravity acts as if it's repulsive due to geometry. In these voids, gravity loses the battle, allowing dark energy to expand those parts of the universe faster. And all these structures were born from tiny quantum fluctuations in the first moments of the universe. These three mechanisms explain why voids exist and how they behave, but this is only part of the story. What about our place within this giant structure? Where are we exactly? And how does this location threaten our most fundamental assumptions about the universe? And this location threatens our most fundamental assumptions about the universe. Because we are not at the exact center of the KBC void, but this does not make the situation better, it makes it even more complex. Measurements indicate that our galaxy is located somewhere about 200 to 400 million light-years away from the true center of the void. This may seem like a huge distance on a human scale. But since the void itself stretches for 1 billion light-years in every direction, this deviation is actually relatively small. We are still deep within the underdense environment of the void, and surrounded by it in every direction. This location fundamentally changes how we see and interpret the rest of the universe. If we were located completely outside the void, in a dense filament, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the crisis known as the Hubble tension would have never existed. The strangeness of this location becomes even more pronounced when we look at our larger cosmic neighborhood. The Milky Way belongs to the local group, which consists of about 80 galaxies. The local group itself is part of the Lenox supercluster, containing roughly 100,000 galaxies spread across 520 million light-years. Lenox is a colossal structure in its own right. But here is where the paradox begins. Even this giant supercluster is located entirely within the KBC void. Stop and think about that for a moment. A structure containing 100,000 galaxies is still considered part of an underdense region. The void is so immense that it can swallow entire superclusters and still remain empty. Lenox forms part of the sparse matter population scattered within the void, one of the rare concentrations in an otherwise barren area. This shows that the void is not a uniform nothingness, but has a structure of its own, just as a desert is not made entirely of sand, but contains small oases. Lenox is our cosmic oasis, but we are still in the middle of a desert. Therefore, even the structure we are in is not enough to cancel out the overall underdensity of the void. This shows just how important scales are. We are part of a supercluster on the scale of hundreds of millions of light-years, but we are inside a void on the scale of billions of light-years. And this complex structure creates another mechanism that affects our view of the universe: observational bias. When we look out from within the void, we're not sampling the universe from a random location. We're sampling it from within one of the universe's most extreme features. This is like trying to understand the surrounding landscape from the bottom of a valley. In every direction you look, you see mountain ranges rising on the horizon, the denser shell of matter surrounding you. This shell appears as a concentration of galaxy clusters and filaments in a specific distance range. Beyond this shell, the universe returns to a more typical density. This creates a systematic bias in our observations. Light from distant galaxies passes through the void to reach our telescopes. This light is subject to fewer gravitational interactions than light passing through denser regions. This creates subtle effects on the light's wavelength and energy. This is not just a theoretical concern. For example, astronomers studying the cosmic microwave background radiation noticed that light passing through voids appears slightly colder. The reduced gravity in voids causes less gravitational redshift, which appears as cold spots in the temperature maps of the early universe. This means we have to live with a systematic uncertainty about how reliable our measurements are. This uncertainty directly threatens one of the fundamental assumptions of modern cosmology, the cosmological principle. This principle states that the universe on sufficiently large scales is homogeneous and isotropic. Homogeneous means every place is the same. Isotropic means every direction is the same. These assumptions allow us to model the entire universe with relatively simple equations. But the KBC void is a major violation of homogeneity. A structure 2 billion light-years wide with a 20% density deficit is not small, even on cosmic scales. What is even more disturbing is that we live near the center of this anomalous structure. This contradicts the idea that our position is noteworthy. The history of science has continuously moved Earth away from a special position. But now, we may have to accept that we live inside one of the largest voids. According to standard cosmology, a void as large and deep as the KBC void should be extremely rare. Perhaps a 10 sigma statistical deviation. In a typical simulation, you might not find a single one anywhere in the observable cosmos. But we are inside one. This suggests either we are incredibly lucky, or the standard model is wrong about structure formation. Both options are unsettling and represent major shifts in how we think about the universe. But what is truly exciting is that all these mechanisms converge at a single point, in a single crisis. And now, we reach the climax of the video, because this void is not just a theoretical curiosity, it is not just a strange astronomical structure. This void is directly sabotaging one of our most fundamental numbers about the universe, the expansion rate of the cosmos. And this sabotage has led to the biggest fight in modern physics, the most unsolvable puzzle. Now the tempo increases, because this is not just a disagreement over a number, this is proof that the universe is lying to us. Here is the first epic moment, the Hubble tension. An impossible contradiction, but it is real. Scientists use two gold standard methods to measure the universe's expansion rate, the Hubble constant. Both are incredibly precise, both have been tested repeatedly, and both stubbornly give different results. The first method looks at the early universe, just 380,000 years after the Big Bang. It analyzes the patterns in the cosmic microwave background light. This analysis says the universe should be expanding today at about 67 kilometers per second per megaparsec. This is one of the most reliable cosmological measurements in history. But then comes the second method. It looks at the nearby universe. It uses standard candles of known brightness, like Type 1 supernovae and Cepheid variable stars. It calculates the expansion rate by directly measuring the distance to these candles and the speed at which they are moving away from us. The result? Consistently around 73. The difference is 9%. It might sound small, but it is a catastrophe, because the error margins have shrunk so much that the statistical significance of this difference has reached 5 sigma. What does that mean? It means the probability of this result being a chance anomaly is less than 1 in a million. The scientific community hit a wall. Something in the fundamental laws of physics was either missing or completely wrong. So how is this possible? How can the universe expand at two different speeds at the same time? This could not be just a measurement error. This was a dagger plunged into the heart of cosmology, and for years, no one could explain why. Here is the second epic moment, the void's solution. While everyone was looking for new physics, exotic particles, or strange behaviours of dark energy? The answer was in a much simpler and much more disturbing place: our own address. The KBC void hypothesis offered an elegant but shattering explanation for this crisis. This hypothesis says the universe is lying to us. More accurately, our location is making us lie. Think about it. We're inside a bubble 2 billion light-years wide, with 20% less matter density. Outside this bubble, matter is denser, so the gravity of the matter outside pulls everything inside outwards. This adds an extra speed, an outflow velocity, to the local expansion. Therefore, in our measurements using standard candles in the nearby universe, we see galaxies moving away from us, not only because of the universe's expansion, but also because of this gravitational pull. This effect artificially inflates the local Hubble constant measurement. The number 73 is not the true expansion rate of the universe. It is the sum of the true expansion rate plus the local velocity field created by the void. When scientists modelled how much a void of the KBC void's size and depth would affect local measurements, they found that the result was just large enough to explain the observed tension. The crisis seemed to be solved. But the price of this solution was sacrificing one of the most fundamental principles of cosmology, the assumption that we do not live in a special place. Here is the third epic moment, the age of the universe paradox. The Hubble tension is not just an abstract number problem, it is a crisis that affects the entire history and fate of the universe. If the value of 73 we measure locally is the true global expansion rate of the universe, and not an illusion caused by the void, it means the universe is expanding much faster than we thought, and a faster expanding universe reaches its present size in a shorter time. This means the universe must be younger. The standard model, based on cosmic microwave background data, and using the value of 67, calculates the age of the universe to be 13.8 billion years. But, if the value of 73 is correct, the universe should be about 8% younger, only 12.7 billion years old. This 1 billion year difference creates another impossibility. Because astronomers measure the age of the oldest stars in globular clusters to be 13 billion years, stars cannot be older than the universe. This is a paradox. This is a violation of the most fundamental rules of physics. Either our methods for measuring the age of stars are completely wrong, or the value of 73 cannot be applied to the entire universe. This age crisis shows why the void hypothesis is so appealing. If the void is inflating our local measurements, then the true age of the universe could indeed be 13.8 billion years, and in that case, stars remain younger than the universe, and the paradox disappears. But this leads back to that unsettling conclusion. To learn the true age of the universe, we have to look outside our own distorted neighbourhood. Here is the fourth and most unsettling epic moment, the collapse of the cosmological principle. For centuries, science has moved humanity away from the centre of the universe. Copernicus showed that the Earth is not the centre. Hubble showed that our galaxy is not the centre. The cosmological principle was the ultimate expression of this process. We are not only not at the centre, there is no centre, because everywhere is equivalent. The KBC void is a direct assault on this principle. Living near the centre of a structure 2 billion light-years wide, with a 10 sigma statistical anomaly, does not fit the definition of an ordinary location. It is, by definition, a special location. This situation puts scientists in a philosophical dilemma. On one hand, there are elegant and universal laws of physics that should be the same everywhere in the universe. On the other hand, there is a statistically impossible local anomaly that causes these laws to give us different results. Which one is correct? Defenders of the standard model argue that rare events sometimes happen, and being inside a statistical outlier is not impossible, just a low probability. But critics say that the KBC void, the Sloan Great Wall, and other giant structures are a sign that the model is failing on large scales. Maybe gravity works differently. Maybe dark matter does not behave as we think. Maybe the universe is much more lumpy and less homogeneous than we thought. The KBC void is not just a void. It is a battlefield where we question our most fundamental assumptions. So what do we have? A measurement crisis that cannot be explained even by a 1 in a million chance. a local anomaly that can explain this crisis but destroys one of our most fundamental philosophical principles, a side effect of this anomaly that throws the age of the universe into an impossible paradox. And all of this shattering the assumption that everywhere in the universe is the same. When all these pieces come together, they lead to one big question. If our location is so anomalous, what other things that we think we know might be wrong? And this question leads us into an even deeper, more disturbing realm, because if our location is so anomalous, everything else we thought we knew could also be an illusion. This is not just about numbers, this is about reality itself. And the most epic evidence for this illusion is not hidden in theories, but in the universe itself, in its largest and most impossible structures. Now, we will look at the real-world reflections of this anomaly, the monsters that push the boundaries of standard physics. Here is the first epic moment, the Eridanus supervoid, a cosmic ghost, but it is real. The KBC void may be huge, but it is not the only monster in the universe. When astronomers discovered a giant or abnormally cold region in the direction of the Eridanus constellation on the cosmic microwave background map, they faced one of history's greatest mysteries. This cold spot was about 70 microkelvin colder and covered an area 10 degrees wide in the sky. This was much larger and much colder than the random fluctuations predicted by standard cosmological models. It was so rare that it could exist with only a 2% probability. The scientific world was stunned. Was this spot evidence of a collision with another universe, or was it just an incredible coincidence? But then, astronomers mapped the galaxy distribution in that direction, and there, perfectly aligned with the cold spot, they found a giant void, a nothingness 1.8 billion light-years wide, on a scale comparable to the KBC void, the Eridanus supervoid. This void could explain about half of the cold spot's temperature anomaly by cooling the ancient light that passed through it. This was one of the strongest confirmations of the theory. The effect that voids leave on the oldest light in the universe was no longer just a hypothesis, but an observable fact. But this also brought another question. If there are two giant structures like the statistically impossible KBC void and the Eridanus supervoid, maybe these structures are not as rare as we thought. Maybe the problem is not with our luck, but with the models that describe how the universe is structured. Roughly 100,000 galaxies spread across 520 million light-years. Lenox is a colossal structure in its own right. But here is where the paradox begins. Even this giant supercluster is located entirely within the KBC void. Stop and think about that for a moment. A structure containing 100,000 galaxies is still considered part of an underdense region. The void is so immense that it can swallow entire superclusters and still remain empty. Lenox forms part of the sparse matter population scattered within the void, one of the rare concentrations in an otherwise barren area. This shows that the void is not a uniform nothingness, but has a structure of its own, just as a desert is not made entirely of sand, but contains small oases. Lenox is our cosmic oasis, but we are still in the middle of a desert. Therefore, even the structure we are in is not enough to cancel out the overall underdensity of the void. This shows just how important scales are. We are part of a supercluster on the scale of hundreds of millions of light-years, but we are inside a void on the scale of billions of light-years. And this complex structure creates another mechanism that affects our view of the universe: observational bias. When we look out from within the void, we're not sampling the universe from a random location. We're sampling it from within one of the universe's most extreme features. This is like trying to understand the surrounding landscape from the bottom of a valley. In every direction you look, you see mountain ranges rising on the horizon, the denser shell of matter surrounding you. This shell appears as a concentration of galaxy clusters and filaments in a specific distance range. Beyond this shell, the universe returns to a more typical density. This creates a systematic bias in our observations. Light from distant galaxies passes through the void to reach our telescopes. This light is subject to fewer gravitational interactions than light passing through denser regions. This creates subtle effects on the light's wavelength and energy. This is not just a theoretical concern. For example, astronomers studying the cosmic microwave background radiation noticed that light passing through voids appears slightly colder. The reduced gravity in voids causes less gravitational redshift, which appears as cold spots in the temperature maps of the early universe. This means we have to live with a systematic uncertainty about how reliable our measurements are. This uncertainty directly threatens one of the fundamental assumptions of modern cosmology, the cosmological principle. This principle states that the universe on sufficiently large scales is homogeneous and isotropic. Homogeneous means every place is the same. Isotropic means every direction is the same. These assumptions allow us to model the entire universe with relatively simple equations. But the KBC void is a major violation of homogeneity. A structure 2 billion light-years wide with a 20% density deficit is not small, even on cosmic scales. What is even more disturbing is that we live near the center of this anomalous structure. This contradicts the idea that our position is noteworthy. The history of science has continuously moved Earth away from a special position. But now, we may have to accept that we live inside one of the largest voids. According to standard cosmology, a void as large and deep as the KBC void should be extremely rare. Perhaps a 10 sigma statistical deviation. In a typical simulation, you might not find a single one anywhere in the observable cosmos. But we are inside one. This suggests either we're incredibly lucky, or the standard model is wrong about structure formation. Both options are unsettling and represent major shifts in how we think about the universe. But what is truly exciting is that all these mechanisms converge at a single point, in a single crisis. And now, we reach the climax of the video, because this void is not just a theoretical curiosity, it is not just a strange astronomical structure. This void is directly sabotaging one of our most fundamental numbers about the universe, the expansion rate of the cosmos. And this sabotage has led to the biggest fight in modern physics, the most unsolvable puzzle. Now the tempo increases, because this is not just a disagreement over a number, this is proof that the universe is lying to us. Here is the first epic moment, the Hubble tension. An impossible contradiction, but it is real. Scientists use two gold standard methods to measure the universe's expansion rate, the Hubble constant. Both are incredibly precise, both have been tested repeatedly, and both stubbornly give different results. The first method looks at the early universe, just 380,000 years after the Big Bang. It analyzes the patterns in the cosmic microwave background light. This analysis says the universe should be expanding today at about 67 kilometers per second per megaparsec. This is one of the most reliable cosmological measurements in history. But then comes the second method. It looks at the nearby universe. It uses standard candles of known brightness, like Type 1 supernovae and Cepheid variable stars. It calculates the expansion rate by directly measuring the distance to these candles and the speed at which they are moving away from us. The result? Consistently around 73. The difference is 9%. It might sound small, but it is a catastrophe, because the error margins have shrunk so much that the statistical significance of this difference has reached 5 sigma. What does that mean? It means the probability of this result being a chance anomaly is less than 1 in a million. The scientific community hit a wall. Something in the fundamental laws of physics was either missing or completely wrong. So how is this possible? How can the universe expand at two different speeds at the same time? This could not be just a measurement error. This was a dagger plunged into the heart of cosmology, and for years, no one could explain why. Here is the second epic moment, the void's solution. While everyone was looking for new physics, exotic particles, or strange behaviors of dark energy, the answer was in a much simpler and much more disturbing place, our own address. The KBC void hypothesis offered an elegant but shattering explanation for this crisis. This hypothesis says the universe is lying to us. More accurately, our location is making us lie. Think about it. We're inside a bubble 2 billion light-years wide, with 20% less matter density. Outside this bubble, matter is denser, so the gravity of the matter outside pulls everything inside outwards. This adds an extra speed, an outflow velocity, to the local expansion. Therefore, in our measurements using standard candles in the nearby universe, We see galaxies moving away from us, not only because of the universe's expansion, but also because of this gravitational pull. This effect artificially inflates the local Hubble constant measurement. The number 73 is not the true expansion rate of the universe. It is the sum of the true expansion rate plus the local velocity field created by the void. When scientists modelled how much a void of the KBC void's size and depth would affect local measurements, they found that the result was just large enough to explain the observed tension. The crisis seemed to be solved. But the price of this solution was sacrificing one of the most fundamental principles of cosmology, the assumption that we do not live in a special place. Here is the third epic moment, the age of the universe paradox. The Hubble tension is not just an abstract number problem, it is a crisis that affects the entire history and fate of the universe. If the value of 73 we measure locally is the true global expansion rate of the universe, and not an illusion caused by the void, it means the universe is expanding much faster than we thought, and a faster expanding universe reaches its present size in a shorter time. This means the universe must be younger. The standard model, based on cosmic microwave background data, and using the value of 67, calculates the age of the universe to be 13.8 billion years. But, if the value of 73 is correct, the universe should be about 8% younger, only 12.7 billion years old. This 1 billion year difference creates another impossibility. Because astronomers measure the age of the oldest stars in globular clusters to be 13 billion years, stars cannot be older than the universe. This is a paradox. This is a violation of the most fundamental rules of physics. Either our methods for measuring the age of stars are completely wrong, or the value of 73 cannot be applied to the entire universe. This age crisis shows why the void hypothesis is so appealing. If the void is inflating our local measurements, then the true age of the universe could indeed be 13.8 billion years, and in that case, stars remain younger than the universe, and the paradox disappears. But this leads back to that unsettling conclusion. To learn the true age of the universe, we have to look outside our own distorted neighbourhood. Here is the fourth and most unsettling epic moment, the collapse of the cosmological principle. For centuries, science has moved humanity away from the centre of the universe. Copernicus showed that the Earth is not the centre. Hubble showed that our galaxy is not the centre. The cosmological principle was the ultimate expression of this process. We are not only not at the centre, there is no centre, because everywhere is equivalent. The KBC void is a direct assault on this principle. Living near the centre of a structure 2 billion light-years wide, with a 10 sigma statistical anomaly, does not fit the definition of an ordinary location. It is, by definition, a special location. This situation puts scientists in a philosophical dilemma. On one hand, there are elegant and universal laws of physics that should be the same everywhere in the universe. On the other hand, there is a statistically impossible local anomaly that causes these laws to give us different results. Which one is correct? Defenders of the standard model argue that rare events sometimes happen, and being inside a statistical outlier is not impossible, just a low probability. But critics say that the KBC void, the Sloan Great Wall, and other giant structures are a sign that the model is failing on large scales. Maybe gravity works differently. Maybe dark matter does not behave as we think. Maybe the universe is much more lumpy and less homogeneous than we thought. The KBC void is not just a void. It is a battlefield where we question our most fundamental assumptions. So what do we have? A measurement crisis that cannot be explained even by a 1 in a million chance. A local anomaly that can explain this crisis but destroys one of our most fundamental philosophical principles. A side effect of this anomaly that throws the age of the universe into an impossible paradox. And all of this shattering the assumption that everywhere in the universe is the same. When all these pieces come together, they lead to one big question. If our location is so anomalous, what other things that we think we know might be wrong? And this question leads us into an even deeper, more disturbing realm. Because, if our location is so anomalous, everything else we thought we knew could also be an illusion. This is not just about numbers, this is about reality itself. And the most epic evidence for this illusion is not hidden in theories, but in the universe itself. in its largest and most impossible structures. Now, we will look at the real-world reflections of this anomaly, the monsters that push the boundaries of standard physics. Here is the first epic moment, the Eridanus supervoid, a cosmic ghost, but it is real. The KBC void may be huge, but it is not the only monster in the universe. When astronomers discovered a giant or abnormally cold region in the direction of the Eridanus constellation on the cosmic microwave background map, they faced one of history's greatest mysteries. This cold spot was about 70 microkelvin colder and covered an area 10 degrees wide in the sky. This was much larger and much colder than the random fluctuations predicted by standard cosmological models. It was so rare that it could exist with only a 2% probability. The scientific world was stunned. Was this spot evidence of a collision with another universe, or was it just an incredible coincidence? But then, astronomers mapped the galaxy distribution in that direction, and there, perfectly aligned with the cold spot, they found a giant void, a nothingness 1.8 billion light-years wide, on a scale comparable to the KBC void, the Eridanus supervoid. This void could explain about half of the cold spot's temperature anomaly by cooling the ancient light that passed through it. This was one of the strongest confirmations of the theory. The effect that voids leave on the oldest light in the universe was no longer just a hypothesis, but an observable fact. But this also brought another question. If there are two giant structures like the statistically impossible KBC void and the Eridanus supervoid, maybe these structures are not as rare as we thought. Maybe the problem is not with our luck, but with the models that describe how the universe is structured. Here is the second epic moment, the Laniakea supercluster, an empire inside a void. This should have been impossible by definition. Superclusters are the densest, most crowded regions of the universe. Voids are the sparsest. A supercluster being inside a void is as illogical as an ocean being in the middle of a desert. But Laniakea is there, a full 520 million light-years wide. It contains 100,000 galaxies, including our own Milky Way, and this entire colossal structure lies completely within the boundaries of the KBC void. How is this possible? This is the strongest evidence that voids are not homogeneous nothingness, but have a complex structure of their own. Laniakea is like an oasis where matter was able to come together locally, despite the void's overall 20% density deficit. But the existence of this oasis reveals even more dramatically how large the desert is. Think about it. Even a structure of 100,000 galaxies cannot bring the overall density of this void close to the average. This shows the overwhelming power of scales. This discovery redefined the question of where we live. We're not just inside the KBC void, we live inside a supercluster that is inside a void. This is a nested series of anomalies, and this means our local physics and observations could be subject to biases on multiple scales, layer upon layer. Laniakea is a shining, but also disturbing, monument to how complex and unexpected the universe is. Here is the third epic moment, the idea of modified gravity. Maybe the problem is not with the voids. Maybe the problem is with gravity itself. This is one of the most radical, most provocative ideas in science. But the existence of structures like the KBC void is pushing some scientists in this direction. The standard theory of gravity, Einstein's general relativity, has passed every test for over a century. But what if it works differently on large scales, over billions of light years? Alternative theories like modified Newtonian dynamics, EMOND, suggest exactly this. According to these theories, in environments where accelerations are very low, like voids, gravity becomes stronger than Einstein predicted. If this were true, structure formation would be much more efficient. Stronger gravity would gather matter more effectively, creating richer superclusters and deeper, larger voids. MOND-based simulations produce structures like the KBC void, not as a statistical anomaly, but as a natural consequence of the theory, the impossibility disappears. This is a very philosophically appealing solution, because it saves us from being lucky observers living in a special place. However, MOND has its own problems. It struggles to explain some features of the cosmic microwave background in particular. Therefore, the scientific community is caught between a rock and a hard place. We will either have to accept that we live in a statistically impossible location, or risk changing a successful century-old theory. The KBC void is forcing us to make a decision between these two uncomfortable options. This is not just an astronomy problem. This is a crisis about the foundations of physics. So what do we have? A second statistically impossible giant void that has left its mark on the oldest light in the universe, a supercluster of 100,000 galaxies within this void, challenging the laws of physics with its very existence, and a radical idea that could explain all these impossibilities, but requires us to rewrite gravity in return. All these pieces of evidence, these anomalies, these crises, are slowly leading us to a bigger picture, a more philosophical realm. The question is no longer, what is there, or how does it work? Now it is time to stop and think. If all this is true, if we're really living in a warped universe, a statistical anomaly, what does this mean for us, for our place in the universe? All these pieces of evidence, these anomalies, these crises, are slowly leading us to a bigger picture, a more philosophical realm. The question is no longer, what is there, or how does it work? Now it is time to stop and think. Because, if all this is true, if we are really living in a warped universe, a statistical anomaly, what does this mean for us, for our place in the universe? When we face this reality, our most fundamental beliefs about ourselves are shaken. And from within this shock, a new understanding of the universe is born, one that is both unsettling and incredibly beautiful. The first paradox we must confront is the contrast between the immeasurable void and the measuring mind. On one hand, there is a nothingness 2 billion light-years wide that pushes the limits of our comprehension. This is a scale so vast that it would take light longer to cross it than the time from the emergence of dinosaurs on Earth to their extinction. Within this void, even structures of 100,000 galaxies like Laniakea are like a single plankton in an ocean. This is the universe's most brutal way of telling us how physically insignificant, how small we are. This is a tragic fact. We are a speck of dust, small enough to be overlooked, revolving around a star in a suburban neighborhood of a galaxy inside this giant void. In the face of the immense size of this void, all of human history, all our wars, all our loves, all our art, remains more meaningless than the blink of an eye. On this scale, we do not exist, and we will never physically reach beyond the boundaries of this void. But, right at this point, comes that magnificent but moment. Yes, we may be physically trapped inside this void, but our minds are not. That 1.5 kilogram organ that evolved on this insignificant speck of dust, the human brain, can measure this 2 billion light-year void. It can prove its existence. It can understand its physics. It can even calculate how it breaks our most fundamental equations about the universe. We may be a physical nothingness, but with our capacity to understand, we become something greater than the nothingness itself. You are part of this paradox. You are that measuring mind inside this giant void. Your body may be as small as a grain of sand in this cosmic desert, but your thoughts can transcend the boundaries of this desert. And this is one of the greatest ironies and most beautiful miracles of the universe. The second paradox is cosmic loneliness and universal connection. Structures like the KBC void show us just how isolating a place the universe can be. The galaxies inside voids drift in a deep darkness, tens of millions of light years away from each other. These galaxies rarely interact, they rarely merge. They are the most extreme examples of cosmic social distancing. This reminds us of the tragic loneliness of existence. If other intelligent life forms exist, it is highly likely that they too live on their own isolated islands, in the middle of this vast nothingness. It is almost impossible for us to reach each other, to communicate with each other due to these immense distances. We are like countless ships, sailing on the same ocean, but never able to see each other. This is a sad song whispered to us by the universe. You are alone. But, again comes that magical but moment. Yes, We may be lonely as galaxies, but as atoms, never. Every single carbon atom that makes you up, every single oxygen atom was forged in the heart of a star that died billions of years ago. So were the atoms in my body. So were the silicon atoms that make up the screen you are watching this video on. The hydrogen from the Big Bang is a common heritage that connects us all. As our galaxy flees the void at 600,000 miles per hour, we travel together within it. The KBC void may separate us from the rest of the universe, but it does not separate us from each other. On the contrary, it binds us even more tightly as passengers on this strange, anomalous, and special ship. You are part of this connection. You are a being made of stardust, and in this lonely universe, you share the same fate with other stardust beings. This is the deepest and most meaningful connection in the midst of loneliness. The third and perhaps most personal paradox is the imperfect universe and the perfect opportunity. For years, we assumed the universe was perfect, smooth, and uniform. The cosmological principle was a reflection of this quest for aesthetic and mathematical perfection. The KBC void is a flaw that shatters this dream of perfection, an error, an anomaly. It is like a scar on the face of the universe. This is a tragic proof of how messy and unexpected nature can actually be. We expected perfect symmetry, and instead, we got a giant asymmetry. This is a disturbing fact for the human mind that seeks order. A fundamental principle of the universe turned out to be wrong, at least for us. This shows how fragile our quest for knowledge is and how easily we can be mistaken. But, again that but moment. This flaw, this anomaly, also created one of the greatest scientific opportunities in the universe. If we lived in a perfect, homogeneous universe, studying the nature of dark energy would be much more difficult, because everywhere, gravity would mask its effect. But this void, this flaw, has given us a natural laboratory where gravity is weakened and dark energy reveals itself with all its power. The Hubble tension revealed a crack, a flaw, in our standard model, and science progresses precisely by studying these cracks, these flaws. A perfect theory is an untestable theory, but this crisis created by the KBC void is opening the door to new ideas, new theories, and perhaps a new physics. You are part of this opportunity. You are a being living in an imperfect universe who has the chance to understand the universe more deeply because of these imperfections. This is the greatest lesson the universe teaches us. It is not perfection, but imperfections that move us forward. So what do we have? A paradox of scale that both trivializes and elevates us. A reality of isolation that both leaves us lonely and connects us to each other. And a cosmic flaw that both shows we were wrong and gives us new paths to follow. All these thoughts show how fragile, yet how meaningful our existence is. But this is only one side of the story. What about the future? How will these giant voids shape the fate of the universe and our own? And this question opens the door to the deepest thoughts about the future, about the fate of the universe and our own. Because these giant voids we live in are not just a part of our past and present, they are also the architects of our future. As dark energy accelerates the expansion of the universe, it also seals the fate of these voids, and thus our fate. And this seal is both a herald of an end and the beginning of a new understanding of the most fundamental nature of existence. The next paradox we face is the tension between the growing nothingness and the shrinking horizon. Right now, even from within the KBC void, we can turn our telescopes and see galaxies and clusters billions of light years away, the dense filaments that surround us. Their light has been reaching us for billions of years. But this will not last forever. This is the tragic truth of the future. Dark energy is expanding space at an ever-increasing rate. This does not just mean that distant galaxies are moving away from us faster, it means that after a certain point, the space between us will expand faster than the speed of light. After that point, the light from those galaxies will never reach us. Our cosmic horizon, the boundary of the universe we can see, will shrink over time. The distant galaxies that shine in our sky today will first redshift, then fade, and eventually disappear completely for future observers. As the voids expand to swallow an ever larger portion of the universe we can see will narrow. Billions, trillions of years from now, for a civilization in our void, the sky will be almost completely dark. But here is that inevitable but moment. This unavoidable cosmic isolation also reminds us how precious the present moment is. We live in that special cosmic moment when the universe is still rich, still connected, still observable. We are witnessing a spectacle that future civilizations will never see. We can see the cosmic microwave background radiation, the proof of the Big Bang. We can measure that the universe is expanding and accelerating. We can map the magnificent structure of the cosmic web. We are living in the golden age when the secrets of the universe can still be revealed. The darkness of the future enhances the value of today's light. You are a witness of this golden age. You are living at a time when the universe is displaying itself most generously. And this is our greatest privilege against the loneliness of the future. This brings us to another contrast: the silent sanctuary and the limited resources. Are voids a sanctuary for life to emerge, or an obstacle? On one hand, the galaxies inside voids evolve in cosmic tranquility. Catastrophes like galaxy collisions, nearby supernova explosions, or gamma-ray bursts that can sterilize planets, which are common in dense galaxy clusters, are extremely rare in voids. This could provide the billions of years of stable environment needed for life to develop. This is the basis for the idea that voids could be potentially safer places for life. But this coin has a tragic other side. Void galaxies are generally smaller, fainter, and poorer in metals. Metal in astronomy means any element heavier than helium, and life as we know it needs heavy elements like carbon, oxygen, and nitrogen. These elements are also necessary for the formation of rocky planets. Since star formation is slower in voids, the production and distribution of these vital elements are also slower. This means voids are resource-limited regions. So, while voids offer a stability that could protect life on one hand, they contain fewer of the basic building blocks needed for life to begin on the other. But, again, that but moment. This limitation might be a driving force for a different kind of life to evolve. Perhaps the life that emerges in places where resources are abundant is carbon-based and competitive, like ours. But in these silent sanctuaries where resources are scarce, perhaps very different, more efficient life forms that we cannot even imagine have emerged. Voids could be the universe's way of telling us the same rules may not apply everywhere. You are part of this equation. You are a life form that evolved in a resource-rich but also chaotic region. Perhaps in those silent galaxies in the voids, a completely different life story is being written under completely different conditions. And this is an exciting possibility about how diverse the biological potential of the universe can be. And finally, there is the paradox of deceptive observation and ultimate truth. The existence of the KBC void has painfully shown us the fact that our observations can be systematically biased. This is one of the biggest fears at the heart of science. What if it is not our instruments, but the place we are looking from that is deceiving us? This is a tragic possibility. It means our entire cosmological model could be built on the misinterpretation of a local anomaly. Maybe the Hubble tension is just an effect of our void. Maybe the cosmological principle is invalid only for us. Maybe the rest of the universe is completely different from what we think. This is a deep epistemological crisis that shakes the foundation of everything we thought we knew. But here is that final but moment. This deception, this illusion, is also the greatest proof of science's self-correcting power. We notice this illusion. We confirm the existence of the void with multiple independent pieces of evidence. We began to model its effect on our measurements. Science does not claim to have reached absolute truth. Science is a process that constantly seeks out and corrects its own errors. The KBC void may be an error in our model, but it is also a key that allowed us to find that error and build a better model. This is a process that makes us more humble, but also wiser. Admitting we were wrong is the most important step on the path to finding the truth. You are part of this process. You are a member of a species that tries to solve the secrets of the universe, a species that can make mistakes but never stops trying. And this quest is perhaps the most meaningful thing in the universe. So what do we have? A destiny that leads us to both an infinite future and an inevitable isolation. An environment that can be both a sanctuary and an obstacle for life, and an observation point that both deceives us and gives us the opportunity to find the truth. All these philosophical thoughts show how complex, how paradoxical, and how special our place in the universe is. We now know not only what the universe is, but also what it means to us. But there is one more question. What happens if we take all this knowledge, this understanding, and apply it to one of humanity's oldest questions? Are we alone? Therefore, it is now time to ask the most profound question. What happens if we take all this knowledge, this understanding, and apply it to one of humanity's oldest questions? Are we alone? The existence of the KBC void makes this question much more complex and much deeper. Because we're no longer just asking, where else could life be? We now have to ask, how can life that emerged in a strange, anomalous place like ours relate to life in the rest of the universe? This brings us to the final layer of our philosophical journey, that deepest realm where we confront knowledge itself and what we will do with it. The first deep contrast before us is the contradiction between cosmological knowledge and unchangeable fate. On one hand, we have the ability to understand the large-scale structure of the universe and detect our own anomalous position. We can understand these giant voids born from quantum fluctuations, their evolution over billions of years, and their physics. This is one of the greatest triumphs of human intelligence and curiosity. We are smart enough to realize that the universe is lying to us. This knowledge itself carries a tragic weight. Because we can also see the future. Our models say that with the triumph of dark energy, the voids will grow, galaxy clusters will break apart, and the universe will become an increasingly dark and isolated place. We know our fate. We know that our galaxy will merge with Andromeda in billions of years, and then this new, giant galaxy will be left alone in the middle of an expanding nothingness, and there is nothing we can do to change this fate. This knowledge makes us both powerful and helpless. We are beings who have solved one of the universe's greatest secrets, but cannot change its outcome. But here is that but moment. Knowing this unchangeable fate also gives us a meaning and a purpose. If we know that the end is isolation and darkness, then the value of the present moment, the moment when the universe is still observable, still connected, increases exponentially. We have an opportunity that future civilizations will never have, the opportunity to learn the full story of the universe. This knowledge transforms us from passive victims into cosmic historians who record, understand, and perhaps will transmit the story of the universe to the next one. You are one of these historians. You are witnessing the most exciting chapter of a story whose end is known, and this testimony is the most meaningful response that can be given to an unchangeable fate. This brings us to the second contrast: individual insignificance and collective meaning. Inside a void 2 billion light-years wide, what can the life of a single person mean? Your troubles, my anxieties, our joys, our sorrows. On this colossal scale, they're all smaller, more insignificant than even a speck of dust. This is an existential vertigo. This is the tragic truth. As individuals, we have no value in the cosmic plan. Nothing we do can affect the expansion of the KBC void by even a millimeter. No one we love can stop the gravitational flow of the Laniakea supercluster for even a moment. This is a difficult insignificance to accept. But here is that but moment. Yes, we may be insignificant as individuals, but collectively, as a species, we are the ones who create meaning. The universe itself consists of meaningless physical laws and random quantum fluctuations. It is a conscious mind that attributes meaning to it, wonders about it, writes poems about it, paints pictures of it, solves its equations. The KBC void has a name because we gave it a name. The Hubble tension is a crisis because we defined it as a crisis. Meaning is not something found in the universe, it is something we bring to the universe. And we do not do this alone, we do it together. Newton stood on the shoulders of giants. Keenan, Barger and Cowi worked on data collected by hundreds of astronomers before them. Science, art, philosophy, they are all a collective project of creating meaning. You are part of this project. You are a cell in that collective consciousness that brings meaning to a meaningless universe. And this is the greatest victory won against individual insignificance. And finally, there is the paradox between the ability to ask questions and the absence of answers. We may be the only beings who can ask the universe why. Why are there voids? Why doesn't the cosmological principle work here? Why are we in this exact strange place? The ability to ask these questions is the greatest gift of consciousness. But this gift comes with a tragic price. Many of the deepest questions we ask may have no answers. Why did the initial conditions of the universe lead to a statistical anomaly like the KBC void? Maybe there is no reason for it. Maybe it is just a result of random quantum dice rolls. The fact that the universe existed before us and will exist after us does not mean it owes us an explanation. This can be the biggest disappointment for a mind seeking answers, infinite curiosity and limited answers. But here is that final but moment. Perhaps the meaning is not in the answers, but in the questions themselves. Perhaps what is important is not knowing everything, but never losing the desire to know. The absence of answers does not stop us from researching, from exploring, from imagining. On the contrary, it pushes us even further. The KBC void did not give us an answer. It gave us a reason to ask better, much deeper questions, and these questions have led us to new discoveries, new understandings. Perhaps the greatest gift of the universe is not the answers it provides, but the questions it allows us to ask. You are that question-asking being. You are part of that unstoppable curiosity that does not stop asking, even when there are no answers. And this curiosity is the most powerful song we sing against the silence of the universe. So what do we have? The helplessness that comes from knowing our fate, and at the same time, the meaning that comes from witnessing it. The insignificance of our individual existence and our power to create meaning collectively. And in the face of the absence of answers, the fact that asking questions itself is the greatest meaning. All these thoughts confront us with the most fundamental truth of our existence. But there is another story to tell. These voids may be hiding one more of the universe's greatest secrets, and this question is directly related to the unique laboratory that the universe offers us to study one of its greatest secrets: dark energy. Because voids are not just a stage for existential thoughts, but also experimental fields where we test the extreme limits of physics. These giant pockets of nothingness may hold the secrets of the mysterious force that determines the ultimate fate of the universe, and solving these secrets is perhaps our greatest task as a species. Therefore, at the final stop of our philosophical journey, we move beyond knowledge itself and face the responsibility that knowledge gives us. This brings us to one last paradox: the cosmic desert and the fertile mind. On one hand, we have the voids, which are literally a resource desert. Places where galaxies are fewer, heavy elements are rarer, and interactions are almost non-existent. This is a tragic limitation. Unlike galaxy clusters, which are the most fertile, most abundant regions of the universe, voids are in an evolutionary stagnation. It is much harder for new and complex structures to form there. This shows that a large part of the universe is an unproductive land, at least for life as we know it. This is a proof of how selective, how stingy the universe can be. The rich chemistry that gives us life is concentrated in only a small 10% portion of the universe. The remaining 90% is silent and motionless. But here is that but moment. This physical barrenness has led to a mental fertility. Precisely because we live inside this void, we have been forced to make some of the most revolutionary discoveries about the universe. If we lived inside a dense cluster, our view of the large-scale structure of the universe would be much more limited. We would see galaxies in every direction and continue to think that the universe is homogeneous. But this void, this anomaly, has forced us to look deeper, to question our assumptions, and to dislodge even a fundamental cornerstone like the cosmological principle. A barren land has given birth to the most fertile scientific thoughts. This anomaly that disturbed us was also the thing that enlightened us the most. You are part of this paradox. You live physically in one of the most barren regions of the universe, but mentally, you're witnessing one of the most fertile periods of discovery in the universe, and this is living proof that even the greatest limitations can give birth to the greatest opportunities. This situation also brings with it the contrast between permanent structures and temporary meanings. The cosmic web, the voids and filaments, seem to be the most permanent, most fundamental structure of the universe. They have existed for billions of years and will exist for billions more. They are the skeleton of the universe. This is the tragic scale of existence. Our lives, our civilizations, are mere flashes in the face of these massive and almost eternal structures. We are temporary. They are permanent. Our search for meaning seems to get lost in the silence of these vast and indifferent structures. Is the existence of a void more important than the death of a human? On a cosmic scale, yes. This is a fact that makes one question humanity's place in the universe, that pushes one to humility. But here is that but moment. These structures may be permanent, but they are meaningless. It is the temporary but conscious beings who give them meaning, who give them names, who stand in awe of their beauty. The KBC void itself is not aware of its own existence, but we are. And this moment of awareness may be more valuable than billions of years of meaningless existence. For even a moment, for the universe to see and understand itself through our eyes, our minds, adds infinite value to this transience. You are a carrier of this temporary meaning. You are part of that miraculous consciousness that brings meaning and awareness to a permanent but meaningless universe, even for a brief moment. And this is the greatest victory of transience over permanence. And finally, the last stop of our philosophical journey, that fine line between the observed universe and the real universe. This is perhaps the most shocking lesson the KBC void has taught us. The fact that everything we see may be a filtered, distorted, and perhaps deceptive version, filtered by our location. This is a tragic uncertainty. Maybe we will never fully know the true expansion rate of the universe, its true age, its true nature. Because we always have to look from within our own local bubble. This means there will always be a but in our quest to reach the ultimate truth. Always a margin of doubt. Always the question, what if we are wrong? This is the most uncomfortable situation for a mind seeking absolute certainty. But here is that final but moment. This uncertainty is also the fuel for science and curiosity. If we knew everything for certain, there would be nothing left to search for, to discover, to wonder about. This uncertainty, this doubt, is what pushes us to build better telescopes, to develop smarter theories, to look into the farther corners of the universe. The difference between the observed universe and the real universe is our playground. This is what keeps the mystery alive, what makes the journey exciting. The KBC void taught us to ask better questions, rather than giving us an answer. And perhaps wisdom is not having all the answers, but continuing to ask the right questions. You are an explorer of this playground. You are a traveller finding your way in a universe without certain answers, with the light of curiosity and doubt. Now we know. We are on a scale that both trivializes and elevates us. We are in a cosmos that both leaves us lonely and connects us to each other. We are in a position that both deceives us and gives us the opportunity to find the truth. And in the light of all these paradoxes, we understand that our place in the universe is not just a coordinate, but also a point of view, a responsibility, and a unique opportunity. As we approach the end of this long and deep journey, it is time to bring together everything we have learned and draw a final picture of what it means to live inside this cosmic void. And so, at the end of this long journey, we return to where we started, us, drifting inside a giant cosmic void 2 billion light-years wide. On this journey, we have seen that 90% of the universe is made of nothingness, that gravity can push in a counterintuitive way, and how our own position sabotages our most fundamental measurements. We have learned that this void is a statistical impossibility, that it creates a paradox about the age of the universe, and how it shakes our most basic cosmological principles, and most importantly, we have realized that this void is not just an astronomical object, but also a mirror that asks deep philosophical questions about our place in the universe, our search for meaning, and our future. We now know that we are not an ordinary inhabitant of the universe. We are inside a giant anomaly known as the KBC void, where matter is 20% less dense than it should be. This fact can explain the Hubble tension, modern cosmology's greatest crisis, because this void artificially inflates our local expansion rate measurements. This is not just a theory. It is a fact supported by multiple independent pieces of evidence, from galaxy counts to cold spots in the cosmic microwave background, from our galaxy's anomalous speed exceeding 600,000 miles per hour to large-scale bulk flows. The universe is not lying to us, but our address is giving us the wrong perspective. You are now a part of this truth. You are that conscious witness on a planet, of a star, of a galaxy, inside one of the universe's largest voids. This knowledge can make you feel both smaller and larger, both more lonely and more deeply connected to the universe. Because this void has shown us not only how big and strange the universe is, but also how miraculous our capacity to understand it is. If this journey has changed your perspective on the universe and your place in it, you can press the like button and subscribe to continue being a part of this community. Because everything we learn opens the door to a new and deeper mystery. These voids may be devoid not just of normal matter, but of something much stranger. On this journey, we saw that 90% of the universe is empty. But there is something I did not tell you. Even the remaining 10% of fullness is in fact almost entirely empty. Because there is something that holds galaxies together, but that we cannot see and do not know what it is. And that thing also controls the fate of these voids. On our next journey, we will investigate that invisible skeleton of the universe, the mystery of dark matter. Are you ready?